We're going to get our first speaker up here, Terry Wallace, known to many of you. He is the Director Emeritus of Los Alamos National Laboratory in New Mexico. He was the Principal Associate Director of Global Security and Senior Intelligence Officer at Los Alamos. He has a bachelor's degree in mathematics and geophysics from New Mexico Tech and a PhD in geophysics concentrating in seismology from Caltech. After that, he taught at the University of Arizona as a professor of geoscience and also applied mathematics. Terry is a fellow of the American Geophysical Union, and he received the AGU's MacLean Medal for his achievements in geoscience. He has served as president of the Seismological Association of America, chairman of the Incorporated Institutions for Research in Seismology, and he is an expert on mineralogy. He's received the Carnegie Mineralogical Medal in 2003 and recognition from many other prestigious organizations. He has published more than 30 articles and many books on mineralogy. So with that, I'd like to welcome Terry Wallace.
So the title of the talk that I get here is Gold, A Cosmic Journey. And I think that as I said, I appreciate to be able to come and talk about gold. And it's something that every single mineral collector admires, right? But I want to give you a little bit different perspective today. It's fairly natural for most of us that are academically inclined in the mineral community to look beyond just the physical aspect of a mineral specimen and think about it in terms of either geology or science or maybe the human interactions. For example, I think that if I was able to give you kind of a crummy polybasite from Comstock, but it had a Mark Twain label, and then I gave you a really good polybasite that just came out of Uchichakwa, you would all pick the Mark Twain label, right? And it's that connection that we can have to a mineral specimen, which is beyond just what you see. On the other hand, mineral specimens are our tactile entryway into this incredible science. So what I'd like to talk about when I say gold is this broader context and take you on a journey which requires an amazing number of miracles that shouldn't happen, such that we get gold on this planet and spectacular gold crystals. And so, the Earth is an incredibly dynamic environment. And we sit here as a third planet in the solar system, and we kind of think of our world as being where we live, but if you look out and you look at somewhere around 100 billion stars or within the Milky Way, and then you have another couple, maybe trillion galaxies, you begin to think about our planet as being not that unique. But in fact, it's incredibly unique. And this incredible uniqueness is manifested even when we begin to drill down and think about our planet within the solar system. Its composition at the third planet out is different than anything that's inside or outside of this in the solar system. It had a water ocean. It has a dynamic Earth that's continued with plate tectonics. Nothing else like that is in the solar system. And all those things begin to have an imprint in what we see geologically. And so I like to think of all minerals as being basically the DNA of our planet. They all have a message. They all have some kind of signature that tells us something about this unique world that we live in. And gold in particular has some really interesting characteristics. These, when I started to think about this talk, and what you see there is 3 nice golds that I have that came out around 2015, 2016 from Mato Grosso in Brazil. I looked at these things and realized that when you actually kind of deconvolve out the crystal structure there, you're looking at huge crystals, perhaps the biggest crystals ever seen in gold, if you actually were able to put these completely together. And I began to think, why are these crystals so big? And what does it have to do with where it was discovered? Well, it just happened to be right at the beginning of a bunch of other discoveries that were completely apparently unrelated in science. But it got me thinking about gold from a perspective of the very beginning of the universe to today. And so that's what I'd like to talk to you about. So I think of this as gold's journey. So when we look at a nice gold crystal, this is another Mato Grosso piece in the center, which is, from there you can look at that and you can obviously tell that that's an octahedron. That specimen is about an inch tall. And when you look at that, it actually is a journey that starts with somehow a creation of an element which turned out not very easy to make. That element had to be created, had to be distributed about the universe, collected in our solar system, put on our planet, deposited as a gold deposit, and then eventually collected. And there's a couple collectors that I want to put in this. Reminds me sort of Scott Werski with his special coat for when he collects in the Yukon. And when we think about that whole picture together of how it works, this journey is really remarkable. So gold is obviously something that humanity's always coveted. There's no way that you can talk about gold, or you just mention it. Everybody knows what you're talking about. It doesn't matter which language you're talking about. It doesn't matter the age of a person. It doesn't matter what their economic status. Everybody's attracted to this metal. There's something magical about gold. And it's not just, as I said, it's not a societal thing alone. There's something about its color, which, by the way, is a really interesting quantum mechanics question to do with how the individual energy of the electrons circulate about the nucleus there. But it also, something about it is just captivating beyond belief. But it's really interesting, our gold journey, really, when we put man at the end of it, is only 7,000 or 6,000 years old. So before that time, all the gold artifacts that have ever been discovered from an archaeological perspective was about a kilogram of gold. So if you go back from anything that's like 5,000 before the Common Era back into history, there's a few gold artifacts, mostly just small films or things that have been pounded together. But an accidental discovery at this place called Varna in Bulgaria in the early 1970s completely changed that. In this cemetery, basically, there was a huge number of artifacts. And that cemetery is about 4,500 years, 4,600 before the Common Era. And there was more than 13.5 kilograms of gold. But we don't see anything before that. But suddenly now it becomes this great ornamentation. Most people don't recognize this name Varna, or even Bulgaria at that matter, but its ancient name is Odessa, which of course shows up in many Greek myths and so on as a place where it's Jason and the Argonauts looked for gold. So it was somehow well known in terms of this, but it was suddenly, and from that date on, gold became something that was very much coveted. It didn't necessarily drive societies like silver did. We'll talk a little bit about tomorrow. Most of the great historical changes in monetary, way you do manufacturing, all those things may be related to silver, but gold was something that became very important in terms of society to own for ornamentation and ultimately as a symbol of a monetary system. The first, also shown on this, is the first mention of gold in cuneiform, and this is a tablet that was unearthed at Ur in the Mesopotamia, and in this thing is a long, long list of commodities. So grain, brick, and all of it is listed as priced in amounts of gold. And so gold appeared in like 3,000 years before the Common Era as a way in which we measure what we own in society. So clearly it's something that's incredibly important to the way we think about this. But the question is, where did all this gold come from? Well, when I say all this, but where did the gold come from? Why is it so attractive to us? What is it about it that makes it so interesting and important? If we look at the mythology of gold, we can go back and see that the first mentions of gold in written text, other than the cuneiform, which was giving it kind of value, describe that it comes from basically the chaos preceding the formation of Earth. So Ovid, which was a famous Greek poet, discussed that this was the elements mingled in the seething mass and randomly and formlessly mixed together in a big gas that was described as the universe to the Greeks before we actually had the Earth. And in this chaos, there was this gas that was gold. And so the first mention is that it does come somewhere outside of Earth. So Ovid may have been an ancient Greek poet, but he's captured the idea that the gold we see today on Earth has a cosmic origin. And this cosmic origin is really what I want to be able to talk about as we go forward today. And so we look at this, when we think about gold coming from the cosmos, you can't talk about the cosmos without going back to 13.8 billion years. You got to go to the very beginning and ask, what is our universe really like? Because everything cares about this thing called the Big Bang, which I have no idea what it is, by the way, but a second after that, I understand it a lot better. So if we look at gold and ask our question, how does this come from the cosmos? And we make a simple diagram which maps through time how our universe changed, we see some remarkable things. The Big Bang occurred. Like I said, very hard to understand exactly what the Big Bang thing. We can do it mathematically, but it's as close as we have to having an article of faith in science. And so once this happened, what we have is the universe appeared through what we call inflation. So something happened, suddenly the universe began to grow at an incredible rate, and we saw this with a hot seething mass, not unlike what Ovid described for the cosmos when he wrote his poetry in Greece. And something like a microsecond after the Big Bang and this inflating universe, we got our first particle that most people would understand, and that's the protons appeared. So we began to have something that's right. And of course, as we'll talk about a little bit later on, protons are a fundamental particle of what we like to talk about, but they're not the most fundamental particle. And we'll talk a little bit of what that means about when we make gold. Maybe a few hundred seconds, maybe a few minutes after that, we began to make a few elements. So we also had to have electrons come along. And so we certainly made some hydrogen at that point. 100 million years, we maybe collected this hydrogen back into big balls and made the first stars. And maybe 500 to million years to a billion years, we began to see some of these balls, these stars, interact in a way that we began to build galaxies. And once we began to build galaxies, then we began to see interactions between these things over an incredibly and continually inflating universe. And then about 4 billion years after this whole thing happened, we saw kind of a peak star formation. And slowly since that time, we've seen less and less stars form, but we've still got a lot of ways to go. So what is all that put together so that we can relate to it as us when we pick up an object, especially when we pick up a gold crystal, for example? Well, let's go think about, when we look at this timeline, let's think about what's really going on in the stars. So when we first started a star and we first collected the gas together, we only had hydrogen. And that hydrogen, in the simplest sense, is a proton and an electron. Later on, we'll get some neutrons in there. And the neutrons are the most interesting thing in the entire universe, but nobody likes to talk to it because their title sounds neutral, neutron, right? But it turns out it's everything, if you're from Los Alamos, you know that we need those neutrons to make nuclear weapons work. And so basically, when we first start these stars, we begin to have new interactions, and those new interactions begin to build other elements. And what we usually think is we think about how stars work. And everybody's had a high school and probably even a beginning college class. In physics, they tell you a star is a furnace which makes other elements, and it makes it through this process of fusion. Fusion is actually a really complicated thing to do. But what we think about is fusion. We'll take a hydrogen atom here with a proton and another proton, and we'll bring them together somehow so they combine together and we make helium. Maybe if I have a helium and another helium, so now I have at least 2 protons, another 2 protons, I'm going to bring those together and make the next element up as we go. The problem with all that is that it turns out it's really hard to make material like that anyway, because the proton has a positive charge, this proton has a positive charge, and if I just go to the laboratory and try to do that, it's going to want to push away. But fortunately, because within that little proton, there are a bunch of strange things, mainly quarks and gluons. And we won't spend the time doing quarks and gluons, but we'll mention it. And it turns out that they give us another force that most of us aren't used to, and that's called the strong force. And it allows us, if we try to push some of these things together, that when we get it close enough, the strong force overwhelms the repulsion, and we can combine those things. And so that's what the process of fusion is. So when we have a star out there, we've combined all this gas. And this gas today contains maybe lots of stuff. But let's imagine those early stars of hydrogen. We bring them together. Gravity is always there. And so as it does, it compresses and compresses and allows us to get things to be overcome the repulsion force, have the strong force work, and we begin to basically release energy by combining these elements to make new, or combining hydrogen to make new elements. And that's what's happening in our star today, the fusion that we have there. But if I really look at this, we have a problem when we try to do this, is that bringing these things together can't be just protons. The only thing that actually makes our whole strong force works is the neutron. So the neutron and its gluons allow us to get these close enough together to overcome. So usually when we think of atoms, we almost always want to talk about a proton and a neutron as a pair, and an electron out there. So we can do this and bring these things together, but even in the best circumstances, eventually we run into this case in which we just have too much repulsion force that the strong force never can occur. And so in the very best stars, and I say best stars, that meaning stars that make new elements that can occur, we get down to around iron and we just have too much repulsion. No star that you see burning in the night sky can make an element that's bigger than iron. So it's filled with neutrons, helping out with all these kinds of things, but we can't make anything that's big, heavier, if you will, than that. And that's not very far up the periodic table. It leaves out all the really good stuff for us, like silver and copper. I mean, silver and gold. It's copper's in there, but silver and gold, okay? So we have to really begin to imagine other things. So we call this process nuclear synthesis, and this is something that we've been thinking about since the 40s. When we first, a guy named Fred Hoyle first came up with this idea that this is how to be able to construct this, and a huge amount of work goes into how these models may work. But it turns out that there are other ways for us in the right circumstances to slowly build other elements. In the laboratory, I can do it by taking an iron, for example, and I can shoot a proton in there at incredibly high speed. If I put it at enough of high speed itself, maybe I can overcome that repulsion, and I can make one element better. But in nature, it's still a complicated process to do that. And it becomes really complicated when we get to the high Z, or the really heavy elements like gold. And so I could go through that process how we do that, but let's jump to gold. Gold is a perplexing problem. Gold is one of the most interesting elements. It's very dense. If we look at its highest density, or it's in the class of the highest density of the elements that are there, it has a relatively modest cross-section, so it's not a very big thing. It's kind of hard to think about exactly what gold is. If I took gold as a single atom and I could make the nucleus itself appear so that you could see it as the head of a pin, then the electrons that interact with it through different energy levels would be a football field away. So when I say it's really dense, it still has a lot of open space in there, but it's way less open space than most elements that are like that. So how can we get there? Well, we're only one way that we know how to do this right now from our mathematical models, and that's to talk about neutron stars. So what the heck is a neutron star? So we know when we make a big star, our star probably is not that big, but it will at some point, the fusion will burn out. So we can't have any more things making. And so what will happen is when we're making fusion, we release energy, and that energy has the sun expand, but the gravity causes it to contract, and so it stays the same size. But as that energy begins to run out, pretty soon gravity will overcome, and so gravity will cause this star to collapse, our star to collapse, and it's a very violent event. If we could make a large enough mass to do this, we could take all those protons and all those electrons and squeeze them together, and a minus and a plus charge more or less gives you a neutron. So there's a class of stars when they finally burn out They finally blow off all their fumes. They do all these other things. We make this thing called a neutron star. And neutron stars are a pretty awesome thing. They're basically a crusty round ball. The mass of a neutron star, maybe 10,000 times that of our Earth, but only have a typical radius of, or look of typical size of New York City. So you can imagine putting all that together there. And it basically is filled with neutrons. And it's a pretty cold place, but it's, this kind of massive thing. But it, being that massive, it obviously still has a wonderful gravitational field about it. And so here's this big universe out here, and we got a couple of neutron stars. Given a long enough time, a neutron star is going to interact with another neutron star. And they're going to feel each other, and they're going to slowly be attracted to each other. And as they get slowly attracted to each other, that's when our really interesting things are going to happen. Now, before I do that, I just want to go back again and talk about gold so that I can make some generalizations in just a moment. As I said, gold is really interesting. It's a great conductor of electricity. Actually, silver and copper and gold all are great. What does it mean to be a conductor of electricity? It means when you put together that material, they just share electrons. They easily flow from one atom to the other. Okay, so it's a metallic bond, unlike an ionic bond that we're used to when we're talking about minerals. Metallic bonds are just kind of things that share, all right? But when you do that, that makes the material have certain properties. They're almost always ductile. So if you look at gold, you can take it and make it the finest wire that's known. So if I take a single wedding ring, about a few ounces, let's just say, a typical men's wedding ring can give you a single wire that is 50 miles long. Okay, so incredible to stretch this thing because it's sharing the electrons as it moves out in this kind of bond. It's very reflective when it does this because electrons moving around give you strong spectra that's coming back. So we got this material that we're talking about, thinking about now, this sharing electrons. It's able to do all these kinds of things. Typically, as everybody knows, when we put the gold together, it gives you a kind of a cubic crystal, and we'll come back and talk about that. But when we have this cubic crystal and we think about the gold there, what we're looking at is these nucleuses that are incredibly dense, a distribution of electron crowds which allow easy sharing, and we have to be able to put that all together. So how do we do that? Well, there's a single process that we know of to make gold. We call it the R process. The R doesn't have any really great name to it. It means rapid, okay? So the R process. And it turns out that if we can take some kind of nucleus, and if I just throw a neutron in there, if I can get that neutron to land, it will probably cause radiation. The neutron will break into neutrino, it'll do some other materials, and my particular material that I shot that neutron in will remain the same. But if I can get enough neutrons in there in a short period of time, some of those neutrons will turn into an electron and a proton. And so I'll change that element. But we have to do that in a really fast time. We believe that gold is made that way, and it's only made when you have very, very specific conditions. And those conditions arise when you have two neutron stars collide. So we have a mass of neutrons and a mass of neutrons, and when they have a violent collision, timescales are small enough that we can collect many of those neutrons into a nucleus that convert to protons, and we can make the heavy elements. We don't know any other mechanism to make this. And so a neutron star collision is something that gives us a chance to make gold. But we're living in a solar system where we're all going and collecting gold, whether it be in the Pacific Northwest or Brazil, and we ask ourselves, well, what does it have to do with gold that we have here? So we're going to have to produce enough gold that we can spread it out this immense universe and be able to recollect it back in our planet and somehow collect it once it's in our planet to make crystals. Let's go back to the neutron star collision. So when these two neutron stars actually collide, it is a very violent process. And when it does, you have a huge amount of ejecta, which comes out, which produces a lot of radiation, but also contains many of this heavier elements. And they're ejected and shot out across great expanses of space. Of course, space in general still is empty. So you're spreading out this gold and platinum and everything else that you made in a short time. But, what does it have to do with kind of this talk? As I told you, we picked up these wonderful gold specimens in 2015. In 2017, for the first time ever, we actually saw a neutron star collision. And when we saw that collision, we happened to have luck on our side in which we were able to actually look at a spectra of the ejecta and see gold and platinum being ejected across the universe. So and we could say that a typical neutron star collision would produce on the order of 500 Earth masses of gold. That's a lot of gold, but the universe is really big. So how did we see that? Well, Einstein was right, surprisingly, and that gravity waves, that's kind of the shape of everything that we are in, shake when you change the distribution of mass in the Earth somewhere. So one of the hardest things to ever teach when you're teaching about physics is what is gravity, because we all know what gravity is. Newton got hit by an apple. So we think of it as this kind of force. In fact, that's completely wrong, all right? And what we're actually talking about is the shape of space. And so what happens when we rotate, the Earth rotates around the sun, it's not because the sun is this massive thing pulling it. It's got a dimple associated with the mass of the sun in a shape of space. And we're circling around this dimple that comes in here in the shape. So what we found is when you look at change the shapes, if we can look at the shape of space, we can see things that are happening. So this event that occurred on a neutron star collision occurred on August 17th, 2017. So we have an instrument in the US at that time, it's called LIGO, and it basically looks at the distance between Louisiana and Washington, okay? That's a long distance, but we're able to measure it incredibly accurate. In fact, we can measure it 1 part in 10 to the 15th. Okay, so what we're looking at is very, very accurate distance between these two places on Earth. And what happened on the 17th of August is that we saw they got closer and further apart. So the entire Earth was changing what we would say is shape. Actually, it was space about us that was changing shape. And this was, a great scientific achievement that was heralded. And one of the leaders of this was this guy named Kip Thorne at Caltech. I happen to have, fortunately or unfortunately, interacted with Kip Thorne for a long time when I was a graduate student because he wanted us to find a way to put seismic stations all around the Earth to look at the shape of Earths to look for gravity waves. We all thought he was kind of an idiot. Because it was impossible for us to possibly make a clock that was good enough to do that. But they figured out how to do this much better in the many years after I left. I wrote him a note 2 days after this occurred and congratulated him, and he wrote a note back and said, "You were this close." But anyway, when this occurred and we saw the gravity wave, it was also recorded on another instrument in Italy, which gave us a possibility to look for a direction. And we swung a number of optical telescopes to look, and we saw ejecta. And that ejecta was very heavy in the heavy elements. So this was our first picture of making these heavy elements that came together. And so the ejecta doesn't mean, the spectra doesn't mean very much there, but it is amazing that we can look at this large distance and be able to see something significant in terms of identifying an element. That's where this gold structure is so interesting. Gold has a very unique spectra. We could pick gold spectra out, carbon, and a few other elements all the way to the edge of the universe. And so we're able to see the gold spectra that was created. So we went from forming this, shooting it out into interstellar media. So now that we have the Webb telescope, we're kind of jaded as a society every time we see a spectacular looking photograph of a nebula or a picture of star formation, because we get great color pictures that we've colorized from Webb telescope, right? So if you look at the Horsehead Nebula, this little picture of the Horsehead, part of the Horsehead Nebula, what we're really looking at is a gas, and that gas contains mostly hydrogen, but other elements. But they all have mass, and as long as they all have mass, they will eventually interact. And under the right conditions, which is mainly time, they can collect and maybe form a new star. Sir Francis Bacon was the first person to propose this, believe it or not. And he said, the interstellar sky hath so much affinity with the stars that there is a rotation of it as well as the star. He proposed that somehow these must collect and occasionally make stars. He had no idea what an atom was. He certainly had no idea what a neutron was. But he proposed that eventually these things we could see with the most rudimentary telescopes in the 17th century must produce stars. So given time, given this material that's out there, we can eventually collect them, and we've now made something like 10, on the order of 10 to the 20th stars in the universe. That's a lot of material. And they've all been there because they had mass and gravity. But that was making the star. How do you make the stuff around stars? And so we think about the formation of our own solar system. So you can think of it as a number of steps. Maybe we eventually have enough material that we've coalesced stuff so that we begin to make a gas ball. And this gas ball, by simple physics, as we pull this together, usually has spin on it. It has to have spin on it, actually, as you do this. The interactions and the mathematics are going to tell you to do this. So what that does is you end up with a disk. And that disk looks like what you see in B. You have most of the mass in the center. That's going to become your star, but you're going to have distribution material, depending on which direction you're spinning around there, which goes from that mass in the middle, which becomes a star, to what for us will be the edge of our solar system. And in that spinning disk, little pieces that are interacting, they're colliding, they're making new material, and we begin to pull, as soon as we put a collision or maybe put together, that has its own gravitational attraction, and we begin to make planets, or things that look like planets. And in our case, of course, we have 8 or 9 planets, depending on whether you're a fan of Pluto or not. And what we've done is collected this material. So we've gone from making material, putting it in interstellar space, making a star, spinning that around, making a solar system, and then we still had to distribute this material within the solar system to make planets. And so we have a couple rocky planets, 4 of them, and then we have some gaseous stuff outside, although they're really pretty, Jupiter and Saturn and so on. And we ask, what's in that material? How did we make that? Well, when we think about Earth, maybe this is a kind of a sequence of how it would be if we have a long enough period to look at it. We collect these things through collisions. As we collect those through collisions, maybe they get together, but then you have gravitational attraction. When you have enough material, squeeze it. If you squeeze any material hard enough, it becomes hot. If it becomes hot, then maybe you can melt some material. If you begin to melt material, you fractionate. So you pull some of the things which are heavier elements, maybe to the center of this mass, and it pushes some of the lighter elements out. And so we end up creating an Earth which is fractionated. For us, it has a core, it has a mantle, it has a crust, and we now have a planet. But this planet is sitting in a solar system which is still under formation. So it's a really violent place to be. It's a bad neighborhood, right? And so we have lots of collisions. We still have stuff shooting across. You can think about, we talk about the meteorite that hit Chicxulub and killed the dinosaurs. That's kid stuff, okay? We had big stuff hit us. We had a big meteorite or a big object hit us that was the moon. It tore some, it's what we call Thoris, it tore some of the material out, but we captured the rest of it, it became our moon. Amazingly, as we fractionated this material, we were bombarding this material, it was like having a large spoon in a boiling pot. We started plate tectonics. Nowhere else in the solar system did we have plate tectonics. But our planet was at the right place, in the right amount of violence. We have this fractionated planet, and it had circulation, and we made plate tectonics. It's amazing to think about that, and we take it for granted, but there's nowhere else in our solar system. We like to talk about our twin being Venus, despite having a really thick atmosphere. There's no plate tectonics in Venus. It just was too close to the sun to actually have enough fractionation that when you began this bombardment that you started plate tectonics. And that's going to be really important for us. And one of the reasons it's going to be really important for us is when we think about what gold is. If we look at the cosmic abundance of elements, it goes kind of like you would expect. Real light things like hydrogen, there's one heck of a lot of that. Okay, that's most of interstellar material. It's a logarithmic scale that's on this little graph that you see here. So hydrogen is by far the most important thing. 75% of the mass of the universe is hydrogen. All right? So when people want to have hydrogen cars, there's plenty of hydrogen out there. And then you see this decay as we come up in terms of the elements in terms of this. And you see up and down. And this has to do with whether you have an odd or an even atomic number, because it tells you something about the neutrons, which tells you about the number of gluons which are interacting. Okay? But you come way down here and you go to something like plutonium or platinum. So for every atom of platinum, there's something like 1 million atoms of silicon. So they're pretty rare. But the heaviness of these kinds of things, they look at this, becomes involved in the fractionation process. So if I look at this, every planet should have an abundance curve that looks like this if you could just grab it out of the universe and make it. But it doesn't look like that. This is how the Earth's abundance looks when we go do everything in the crust. And we look at the elements in the crust. Gold is the 72nd most common material, but it's way down there. It's in that little yellow section at the bottom there. Its abundance is way below what we would expect just from the cosmic or the universal abundance of gold. Why? Because being heavy in a fractionated Earth, most of our gold, 98.5%, is in the core. Okay? So most of it's pretty inaccessible. Somebody will eventually figure out how to get to the core, but I don't know. But we obviously have gold deposits. And when we look at gold deposits and we look at the rest of the crust, we know that we have continual renewal of gold. Part of that comes from processes which bring mantle plumes up and bring new material from deep in the earth. But an equally important part is that for that period of time early in the earth, after we had already fractionated, but we started being invaded by these large things like the moon, we had a number of meteorites deliver gold to us also. So it's in our crust, but it's well mixed. When we say it's the 72nd most common mineral or common element, can you imagine if you had to mine everything and it was only that abundance? But plate tectonics really helps us out by being hot. It recirculates material, in particular things which are heavier Zs, heavier, and it gives us a chance to collect things in mineral deposits. So as I say, thank God for plate tectonics. When we think about plate tectonics, of course, we're thinking about a process in which we're continually renewing the surface of the Earth. And so we have old continents, but we have oceans, no oceans much older than about 200 million years. And that conveyor belt is bringing material up, but it's also causing things to remelt. And we're taking that 72nd most common element and melting everything around it and beginning to collect it in mineral deposits themselves. And so plate tectonics gives us rise to several environments in which we can begin to collect gold. All gold at some point all gold deposits were part of a redistribution of things associated with plate tectonics. So we have gold in many different environments today, but they all had to have been recollected, erupted, made into new deposits through the plate tectonic process. So when I look at this is kind of, again, every geologist has to have lots of pictures showing plate tectonics and showing a building of a mountain range. What the real purpose of this is to show is that given our long history, and remember the key is plate tectonics, we've built many collisions, many subduction zones. And so all those subduction zones at some point had a recollection and probably had gold deposit. For America, or the United States, the most famous of these collisions occurred to give rise to the Sierra Nevada. So the next talk we'll talk about the mother lode. That is a process in which the plate tectonics have redistributed the gold and put it together to make a wonderful deposit. If we did not have plate tectonics, we would never have gold deposits. So this is an example, again, looking at the different types of deposits, and I won't go into detail on this, but there's lots of ways to have gold interact with different things. And so we can put gold then in a hot environment and we can make many different deposits. The only important part is plate tectonics, but the details can be very different. There's three things in the details I want to come back to. One of them is that when we interact with other rocks, we're always going to have a condition called EH or pH. So you're going to have acids or you're going to have bases. All those things are going to be the thing that actually controls the chemistry. And so how gold turns into a deposit depends upon the interaction with the rocks that are surrounding it. The second thing that I want to talk about this is that no matter where you put it, no matter what kind of mountain range you make, geology tells you that time always wins. And since we have a liquid earth, mainly oceans and lots of atmosphere, eventually every one of these deposits is going to erode. And that will cause a new redistribution of where the gold is. But the gold, being very heavy, will have a number of characteristics. And the final thing that when we look at this is that we can actually almost always tell you where gold will be if we understand geologic history. Okay, so wherever I have a tectonic collision, I'm going to get gold. This is my favorite gold specimen I personally own because it's from Scotland. And it's probably one of the finest Scottish golds known. That really doesn't say very much, but it's formed by the collision associated with what is today North America and it's Europe that occurred 450 million years ago. And across Scotland, through into the US, in Vermont in particular, and in New Hampshire, there was a belt that was not unlike the mother lode belt that you see in the Sierra today. And so when I look at this, you could see the quartz, which is often the thing that delivers the gold, and my cross-sectional there is a mother lode vein system. So quartz and gold are going to be really important for the last part of our story. This is a picture of some other golds. I own a couple of these, but not all of them. They're from Irish Golds, which was very near Bonanza Creek, which was the original discovery of the Yukon gold rush. And you can see great crystals that are going on in here. So what can I tell you about the crystals that I expect to see and this process of plate tectonics? So when I see a wonderful crystal like that, or the pictures that I showed you for the Brazilian golds, how many people would suggest that if they're big, it must have taken a long time for them to grow? I think that's the normal reaction, but it doesn't. I'm going to show you that probably those large gold crystals grew in less than a minute. And it's because when we drop the gold out of this solution, and it doesn't like to stay in a solution, probably has chlorine or something else, the EH-pH, interacts with the rock type. When it drops out, it grows crystals incredibly fast. So some basics for the way crystal growth works. If we look at this, we have usually think about crystal growth as a driving force, how much material you're putting into it, versus something that looks like the amount of material that's in a solution. So we can think of slow over here by the axis to fast as we move out. We can look at any material. We do lots of experiments with this with lots of different materials as we make semiconductors and so on. But what we usually see is if we're growing a crystal very slow, we usually make a fairly smooth surface and the crystal grows. Think about a cubic crystal. That's why gold's so interesting. If you think about this and you, from a simple thinking of energy, if I'm going to make that crystal grow, I have to make the entire face grow out if I want that crystal to be smooth in all directions. But think about the corners. The corners sit here, and in 3 different directions you can add a material to the corner. So if I have to add material fast, the corners grow much faster than the center of the crystal. And that gives us strong hoppered crystals. So most of the crystals we just saw, and I'll come back to the Brazilian ones, are all hoppered. And our experiments in the laboratory tell them to build that strong of a hopper, not harper. We have to be able to do it under time scales, which are, as I said, minutes at most. What we know most about crystals that we do in the laboratory all the time is do it with water. So that doesn't sound like a really good thing to be comparing to gold. But in fact, we can make and control exactly how we grow an ice crystal in the laboratory by fine tweaking things and use this as an analogy for us to understand gold. So let's go to from ice here to gold. Here's a couple of these crystals. So these are, I have an octahedron, I have something that looks kind of in the middle of a cubic, and then this kind of crystal is obviously kind of diagnostic for these crystals that are coming out of Mato Grosso right now, in which there's lots of kind of layers, and it almost always is this triangular. And above that, I show you a simple schematic. In one part of this thing, I'm showing you going a cube, we're growing the edges, and what we end up with, we leave the center behind, but the edges grow out, and so you end up with a cubic crystal that looks something like this, with a big hole in it. That is exactly what we're seeing in that last picture of the Mato Grosso. If we slow that growth down a little bit, we can get the middle one, which is cubic, but still pretty hoppered. And finally, for us to get to the octahedron, we're probably having the slowest growth possible. That slow growth still is hours at most, but maybe not minutes. So when I look at these crystals and think about this from the Brazilian, I now have a way to almost get to the end of where I want to get in this talk, and that's the interaction of how we think about these things. But the last thing I want to say is, we had the crystal grow fast, but how did the gold choose to grow there? If I melted a bunch of rock and I collected gold, I still have a pot of stew. How do I move that? And almost all of it's moved by quartz veins. And there's a reason for that. Number one, silica is the most common crustal element. But another one in this is that quartz grains, or quartz when we melt it, which is very easy to melt, by the way, almost always contain impurities, and some of those impurities are almost always a little chlorine. Chlorine is one of the few things that keeps gold in solution. Gold doesn't want to react. The other is CO2. And so maybe you can imagine an environment where you're high in CO2. But if you take that solution, and we got quartz here, we're injecting that to material. So we're making new veins. We do that rapidly. But as we do that, we can suddenly touch different rocks of different types. And if we touch a rock that changes the EH or pH, the gold falls out of solution. So it's the making of the veins that provide the gold to come out of solution that this can suddenly rapidly grow that crystal. So if I look at all the different kinds of veins that I see, inevitably, when we're looking at this, we can see wonderful gold crystal. There's the famous Minji cooling gold from the San Juans. They're going to be in a quartz vein. And it's the interaction that had with a country rock that did that. So there's lots of different cases in which we look at this. And so what I want to leave you with that is that you still have to have this condition that you can make quartz veins and then they can travel rapidly and suddenly drop the gold. And of course, I said before, you're going to eventually erode that material. But gold is wonderful. And so almost all gold will stay in the environment that way as gold. and you end up with placer deposits. And of course, every discovery previous 50 years ago all started with a placer discovery, right? Every one. They went out and they plastered in, you basically look for gravitational traps. This is my single favorite specimen that I would love to own, but I don't. That's the Weimar nugget, which was found on January 24th, 1848 by James Marshall, or his crew, actually, at Sutterville. And so this is in the Bancroft collection at UC Berkeley. And the reason this nugget is so famous is that about a dozen nuggets was collected that first day, but they were unsure if it was really gold. And so they divided it up into 3 different people, and they all took it, to do their own test to see whether it's gold. Weimar gave it to his wife, and his wife boiled it in a pot of lye, which was also their soup pot. So sometimes they called this the soup boil. And this is that nugget. It didn't dissolve after being boiled for X number of hours. And so this little nugget is the thing that's the human connection to the greatest mass migration in the US history and changed our country completely. In 1849, there was people that are like us, what we call Americans, in California was less than a few thousand. By 1855, it was almost 1 million. And it was all driven by the desire to look for this gold. So let me go back to the Brazilian ones. Another collision that occurred was between South America and Africa. And this collision occurred about 800 million years ago and gave rise to what must be the analogy to our Sierra Nevada. And the middle kind of figure there shows how that collision went together. So you would imagine that collision where you see that suture is a region that you would expect to have large remnants of this collision. And in fact, that's where the great gold deposits of South America are. So whether they be along a craton in Venezuela for those golds or these in Brazil. But when we go there today, remarkably, especially if we go to this Mato Grosso deposit, this is what it looks like. So the first figure that you see over there is actually looking down on this in 2016. And those are all individual prospectors, illegal, I'm certain, at this point, all digging a hole in basically soils. And they're finding gold, but it's crystallized. This is an example of the Earth's surface. And if you look at this, we call this material which was originally holding the gold. You can imagine granites with with quartz and everything else as being where it was. If you gave 800 million years and you didn't move it around, you form a saprolite. And this is just basically mud or clay or decomposed granite. But the gold doesn't decompose. And so they're digging holes without any knowledge of what the geology is in the hope that they run into gold itself. And in fact, these wonderful crystals that we see here are all found with no matrix, but still well crystallized, so they didn't tumble down a stream when the material was decomposed. So the gold was formed about, 6 billion years ago in a cosmic event, neutron-star collision. Much of that gold traveled to Earth and meteorites and so on. The gold was formed about 800 million years ago, and we can find that today. So when I pick that up, I have to realize that my story is a story that is that long and that miracle laden. And my last slide is just every gold has a human story. So the last human story is a little piece of gold that is on pyrite. It's from New Mexico. It's about 40 miles from my house. And this is the first gold rush west of the Mississippi to come to New Mexico to look for this gold. And so to me, that specimen is the most valuable one that I own because I can relate to it. So I leave with that. This is a true cosmic journey. Don't look at gold just as an object. It's from physics to human tactile. Thank you.
We can take a few questions. I want to get us, keep us on time. Yes, Paul.
So were the LIGO-based observations a confirmation of the existing hypothesis, or was there a different hypothesis before the observation?
Can you repeat the question?
Yeah, so the question is, when the August 17th observation was made, is it a confirmation of theoretical fact, if they will, versus unobserved? And so that's a great question. The fact of the matter is that our mathematical models for what should have happened with a neutron-star collision were confirmed to the 99th percentile. What was the surprise about that is that the next generation of LIGOs, which is in right now, we're now able to see things happening between, so neutron star will give you one kind of ripple, but a black hole interaction will be a different one. What we now have is a catalog of around 25 different kinds of interactions that we can observe for the edges, the very edges of the universe. And it's, you know, it's like having a telescope, except it's a different kind of thing. And it's amazing that we can be able to do that. So almost all the black hole observations that are talked about now, some of it's observational from like telescopes seeing absence of light, but most of it is the interaction it has with other material, which we can now begin to see on these long baselines.
Okay, Ray, I saw your hand up. Yeah.
Just a quick question. Crystals, as far as I know, are only a little tiniest tipping point of the spectrum of all gold that's found. So is it still believed that there's a bacteriological involvement in the accretion of gold in nuggets and other locations?
So that's so the question that's asked is much of the gold that's found is very fine grain, and there's been a long discussion that there's a biological element for collecting that gold. And I would say that we don't really have a good resolution on that. Certainly gold nuggets, and we look at these huge nuggets from Australia, right? When we actually take those to the laboratory and we look at neutron scattering for that, what we see that those are a compression of many smaller pieces of gold. So there's an accretion process to making most nuggets, to be perfectly honest. But the fine, a Carlin type deposit, there is carbon almost always in that. So we think that there may be some biological component, but I don't believe that that we really have a good resolution of that.
Okay, one last question, and then we need to go to break.
I've seen pictures of wire gold from, I guess, Australia. Are those actually crystals, or are they pseudomorphs of silver?
So wire gold is a conundrum. So if you'll listen to the talk tomorrow, I'll tell you why silver wires are easy to grow, because they're the first ionic superconductor, right? Gold isn't. We think of gold as being a great conductor, but compared to silver, it's a piker. Okay, but what you have to grow a wire usually is to take the gold out of something. So when we grow silver wires, we take it out of a myriad of sulfides. We don't have very many gold sulfides. We have a lot of gold tellurides. So we've been always looking for this, and Scott has said this, we can find gold wires, but very, very small out of tellurides. But then somebody comes in and they say, oh, I'm from Harvard, and they throw down the groundhog gold, right? And it's like, well, I don't know what it is. And we don't actually have a good model for how to grow large gold wires.
All right. Thank you very much.